Pythagoras' theorem, the means by which we can work out the third side of any right-angled triangle so long as we know the other two. Now let's just take an example of a right-angled triangle here. We know it's a right angle because of the square angle notation in the corner. Now if we were to then just label this side A, this side B, and this long side C, it's important that the long side be what's labelled C. The A and the B really can go either way around. Now if we have this, Pythagoras' theorem states that we can say A squared plus B squared equals C squared. So this length here, squared, added to this length here, squared, would equal this length here, squared. But what can we do with this then? Well, if we just give ourselves another right-angled triangle here, label this side 3 and this side 4, with this third side C being an unknown for now that we're trying to work out. Well, based on Pythagoras' theorem, we should be able to say that 3 squared plus the 4 squared will give us this other third side, also squared. Well, 3 squared is 9, 4 squared is 16, and together they're going to give us 25. Well, what's 25 expressed as something squared? That would be 5 squared, meaning that this C here is in fact a length of 5. Now it doesn't always have to be with whole numbers. If we just wanted to create another triangle over here, we could say that maybe one side is 6.7 and the other is 4.9. Again, we could just say that the 6.7 squared plus the 4.9 squared is going to be what gives us this third side here. And you don't have to do all of this term by term. In your calculator, you can therefore just say, or type in, what is the 6.7 squared plus the 4.9 squared, and it will give it that the solution will be 8.3. If we then wanted another example, we just draw ourselves another right-angled triangle. The sides don't actually have to be whole numbers, and in fact most often they may not be. So let's say this is 6.7 here, and this is 4.9. Again, with the long side being the thing that we don't know. As before, we can just set this up to say that 6.7 squared add the 4.9 squared is going to be what gives us this squared. And now you don't actually have to work these out individually this time, of course you can, but to save time, you could just put it all in your calculator at once, and putting it all under a square root already, as that's what you're going to need to do to get rid of the square from the C. Plugging this into your calculator to one decimal place, because that's what these are, well, this would give us a length of 8.3. Now, it's quite possible to use this Pythagoras theorem to work out one of the other sides, either the A or the B of a triangle rather than the C. So if we were to start instead, just triangle can be done either way around, where this is 13 and this is 5. Because the 13 is in the place of the C, and say the 5 is in the place of the A, if we were keeping this notation the same way around, to get what's on the bottom, the B, we'd actually want to move the A squared over to the other side, making it a minus A squared. So here it'll be 13 squared minus 5 squared. And again, if we wanted, we could go straight into that square root, and that gives us that this third side here would in fact be 12. So if you're after the long side, the C, you'll be adding, but if you're after either of the other sides, you'll minus. Let's see how you can get along with an example of your own, therefore. Just over here, if we were to draw one more triangle here for now, where this is going to have a length of 9, and this is going to have a length of 10, can you work out what this third side here is going to be? And then also, we can check if that's right by then doing the reverse of that answer squared minus, say, the 10 squared, leaving you with what 9 squared would be. If you just want to pause the video here to have a go for yourself, we'll then walk it through to see how. So, if we had used the theorem in the same way you had before, where we'll be doing our square root of 9 squared and 10 squared, you should get an answer of approximately 13.5 or 45, depending on how many decimal places you did it to. We didn't specify in this question. If the question did say like 3 significant figures or 3 decimal places or anything like that, you would know exactly what level of precision you need to give it to. If we were then testing this, if we just took our 13.45, let's say, you want to be as accurate as possible, try to keep as many numbers in the calculator as you can, even if you don't write them all on the page. If we do that number squared minus, say, the 10 squared, all square rooted, that should get you back to 9. Okay, so if those are the basics, let's just move on to an actual example question. And we can see here, while the principles of the Pythagoras theorem are going to be the same, the question is presented in a slightly different way. We're just going to have to do a little extra step. So here, the question tells us we have a trapezium. We've got 2 parallel sides, some distance between them, and a slant. It says AD is 10, AB is 9, and DC is 3. And these angles here are 90 degrees, as again represented by the little squares in the corners. And it would like us to work out the length of A to C. Now, in order to work out this, we're going to have to do a few more steps. First of all, we're going to have to work out what BC is, because then we can make a right-angled triangle out of ABC. But before we can get BC, we're actually going to want to get what this length is going to be, where that makes this a right-angled triangle on top. Now we can see here that our C, our long length, the length opposite the right angle, is 10. But as for our height, our A, if this whole length here, AB, is 9, and this here is 3, that leaves this here just being 6 centimeters. So, as we work this out, we'll say that it's the square root of 10 squared minus 6 squared, which will be the root of 100 minus 36, which is root 64, which is 8. Okay, well now that we have this side, I'm actually just going to rub out these bits here just so we have the space. If we now join up A and C to now make this right-angled triangle, as I said, the triangle ABC, we can now say that, okay, our A value is the 9, and I'm going to plus our B value of 8. So it's going to be 9 squared, add 8 squared, square rooted, which is not going to come to a nice number this time. If we do it in the calculator, we're going to get that as approximately 12.0. And I bothered to do the 0.0 because the question did specify to 3 significant figures. On the calculator it is 12.04. The 4, which would be the 4th significant figure, rounds down, just leaving it as our 12. I might as well label that centimeters. And that would be our answer. This we have got by doing 2 versions of Pythagoras' theorem within a more complicated shape.